Half-life is the exact amount of time it takes for half of a radioactive sample to spontaneously decay into a new stable element. So the thing about half-life is it's completely constant. Every radioisotope will have a specific half-life. That half-life cannot be changed. It can't be sped up or slowed down with things like heat or pressure or chemical reactions. So it's completely unchangeable depending on what a radioisotope is. You have table N, which gives you a long selected radioisotopes list. In the first column, it'll tell you what that radioisotope or that nuclide is. It gives the symbol and the mass number for that radioisotope. The next column gives you what the half-life is. So to just review, we have milliseconds, seconds, minutes, hours, days, and years. Milliseconds would be the shortest half-lives, and those would be very fast. So that means that if something has a short half-life, something like calcium-37 has a half-life of 182 milliseconds, that is super fast and it will decay very fast. If a half-life is for days or years, that's the longest half-life. So it takes longer for those to occur. So looking at carbon-14, carbon-14 has a half-life of 5,715 years. So it takes a very, very long time for carbon-14 to break down and decay. What is the half-life of the radioisotope shown on the graph? In this graph, we have a decreasing curve. We have time on the x-axis and a percent of unstable isotope remaining on the y-axis. At time 0, where our curve starts, we have 100% of our sample, 100% of the sample as a fraction of 1. We can use this graph to determine what the half-life actually is, because when we go from 100% to 50%, the sample is losing half of its mass. The amount of time it takes to reduce half its mass is the half-life. We can look over until we hit our curve and then look down to find how much time that was. So the half-life for this sample is 4 minutes long. To answer half-life questions, we're going to use our table setup like this, where we have HL standing for the number of half-lives, T standing for time elapsed, M standing for mass, and F standing for fraction left. Every time we're going to start out our half-life column at 0 and go up to 4. Time that has elapsed when no half-lives has occurred will be 0. And fraction left at 0 half-lives would be 1, standing for 100% of our sample is still there. After 1 half-life, we would have half of our sample left. After 2 half-lives, we would have a quarter of our sample left. After 3 half-lives, we would have an eighth of our sample left. And after 4 half-lives, we would have a 16th. The half-life of iodine-123 is 13 hours. How much of a 64 milligram sample of iodine-123 is left after 26 hours? The first bit of information is the half-life. So it says 1 half-life for iodine-123 is 13 hours. So you're going to put 13 hours in this box here, okay, right next to where it says 1 half-life. After 1 half-life, 13 hours has passed. It also says that we have a 64 milligram sample to start. For our starting mass, we're going to put that on the top in our mass column, okay, when we have 100% of our sample before any time has passed. Now we're going to work down our columns and fill out the rest of this information. So for our time column, we're going to take the amount of time for 1 half-life, so 13 hours in this case, and multiply that by the number of half-lives. We'll do 13 times 2 half-lives to get 26 hours. After 3 half-lives, we would multiply that by 13, our 1 half-life, to get 39 hours. And then for 4 half-lives, 4 times 13 is 52 hours. Because after each half-life that occurs, it's reducing half of its mass, we're just going to divide our mass by 2 each time we go down. If we start out at 64 milligrams, but then 1 half-life has passed, so 13 hours passes, that means our sample is going to reduce in half down to 32. After 2 half-lives, that's going to reduce in half again, 16 milligrams. After 3 half-lives, reducing again to 8 milligrams. And then lastly, after 4 half-lives, it's going to reduce one more time to 4 milligrams. So what we're trying to figure out is how much mass is left after 26 hours. We find 26 hours elapsed right here, and we can just look over in our chart, and we found that 16 milligrams of that sample will be left. Starting out our table the same way. For half-lives, we go 0 to 4. Fraction, we go 1, 1/2, 1/4, 1/8, and 1/16. And then we can start out with time 0 as well. How long, so how much time will it take for 30 grams of radon-222 to decay down to 7.5 grams? It says we have a starting or original mass of our sample of 30 grams, so we can place that in our table. And now we have to write in what our half-life is. This is one of those times where if the question doesn't give you a half-life, and that's not the variable that you're trying to solve for, you probably have to take a look at table N to find what the half-life of that radioisotope is. We would look up radon-222, and we'd find that its half-life is 3.823 days. So we'll plug in 3.823 days in for one half-life of this radioisotope. Now to fill out the rest of our column, we're going to take the amount of time for one half-life and multiply that by the number of half-lives. So 3.823 days times 2 gives us 7.646 days. 3.823 days again multiplied by 3 will give us 11.469 days. 3.823 days multiplied by 4 would give us 14.292 days. To work down our mass column, we start out with original sample of 30 grams, and each half-life it's going to reduce in half. 30 divided by 2 is 15. 15 divided by 2 is 7.5. 7.5 divided by 2 is 3.75, and 3.75 divided by 2 is 1.875. Could have stopped here if you notice that we didn't have to do any more. So sometimes you'll start to notice that you don't have to fill out the entire table to find your answer. But we want to write down how much time it takes for our sample to decay down to 7.5 grams. So we look at the time that has elapsed when we have 7.5 grams left, and we find that it is 7.646 days. How many grams of nitrogen-16 will be left from a 16-gram sample after 21.39 seconds? Our original sample is 16 grams, and we want to figure out how much is left after 21.39 seconds has passed. We're going to look at table N, and it is 7.13 seconds. So we'll put that half-life for nitrogen-16 in our table under one half-life. We multiply one half-life by the number of half-lives. 7.13 times 2 is 14.26. 7.13 times 3 is 21.39. So again, we could stop there. And 7.13 times 4 is 28.52 seconds. We start out with 16 grams. After each half-life occurs, it's going to reduce half its mass. 16 goes to 8, 8 goes to 4, 4 goes to 2, and 2 goes to 1. How many grams are left after 21.39 seconds? That will be 2 grams. What is the half-life of a radioisotope if 25 grams of an original 200 gram sample of the isotope remains unchanged after 11.46 days? This is a question where we don't know the half-life of the radioisotope, but this is what we're trying to find. So we're trying to find what goes in this box right here. Now it does tell us that the original mass of our sample is 200, so we can plug that in. We know that once that sample reaches 25 grams, 11.46 days will have passed. Okay, so we're going to have to work backwards to find what the half-life is. We can start by filling out our mass column though. If we have 200 to start, after one half-life, 200 divided by 2 will give us 100 grams left. Then after 2 half-lives, 50 grams left. After 3 half-lives, we will have 25 grams left. Then after 4 half-lives, we will have 12.5 grams left. When we have 25 grams, 11.46 days will have passed. We can put in 11.46 days next to where it says 25 grams. So that means 3 half-lives has passed, and this is when the sample has reduced to 1/8 of its original mass. Before, we were taking one half-life and multiplying it by the number of half-lives to figure out how much time has passed. To figure out what one half-life is, we're going to do the reverse. We're going to take the amount of time that has passed, divide it by the number of half-lives that is. So that was 3 half-lives passed. And that number is going to be our half-life. So 11.46 divided by 3 gives us 3.82 days. So for this one, we found the information that we needed. So it's okay if not all blanks are filled, where it's not necessary to fill them, because this is the only number that we're trying to solve for. There are 5 grams of iodine 131 after 32.084 days. How many grams were in the original sample? This time we're trying to find what number goes in this box, okay, when we have 100% of our sample before any time has passed. The question is giving us iodine 131, so we have to make sure that we look at table N to find the half-life, and it is 8.021 days. So we can plug that in for our 1 half-life. Now we want to see how many half-lives passes to reach 32.084 days so that we can then work backwards and figure out what our original mass is now. So we'll do the same process as before, where we multiply 1 half-life by the number of half-lives that it is. So 8.021 days times 2, 16.042. 3 half-lives times the amount of time for our just 1 half-life, 24.063 days. Lastly, 8.021 times 4 will give us 32.084 days. 32.084 days is when we have 5 grams of the sample. So now to get back up here, before to get down the mass column, we divided each number by 2. So now we're going to do the opposite. We're going to multiply each number by 2. After 3 half-lives, we would have had 5 times 2. So we would have had 10 grams left. After 2 half-lives, you're going to multiply by 2 again. So 10 times 2 gives us 20. Multiply 20 by 2 to get 40. And multiply 40 by 2 to get our final mass of 80 grams.